Now let's see this question. How many n state DFAs can be constructed with a designated initial state over sigma, over the alphabet sigma, containing m symbols? Now what they are saying is the number of states we have is n. Okay, the number of states is n and the number of symbols in sigma is m. So this is what is given. Okay, now let's try to draw the skeleton, the structure. So if you are going to have n states, the table is going to look like this: 1, 2, 3, 4, 5, so on. N states are going to be there, right? And one of them is already designated. It is having a designated initial state, which means once you make a state as initial state, you are not supposed to change it, right? Let us say state number 1 is initial state. I am not going to change it throughout my explanation, right? And the next one is sigma is containing m symbols, right? Therefore 1 symbol 1, symbol 2, symbol 3, so on, m symbols are here. Okay, now this is the outline. Okay, now how can, see, first thing is how many such structures are possible. Second is, once you draw the structure, how many ways we can create a DFA by filling these entries. Okay, these two have to be examined. Now let's try to find out how many such structures are possible based on the final state. If you have 0 final state, this is the only structure possible, right? So if we have one final state, which one can be the final state in this? Any one, right? So if I don't choose any one of them as the final state, I'm going to get one final state, one structure. It represents NC0, which means I'm not choosing any one of the states as the final state. Or you can choose any one as the final state, NC1, or you can choose any 2 as the final state, or you can choose any 3 as the final state. Finally, you can choose all of them as final state, right? So these many structures are possible. Okay, and now for every structure, how many ways we can fill the table entries is, first you find out how many, what is the size of this table. The size of this table is m into n, right? And each entry in this table can have n ways of filling it, right? So here one of n elements can be present here, one of n states can be present here, here also one of n states can be present here. Therefore each one is going to have n options, right? So I am going to have n into so on, m into n times, isn't it? Therefore it is n power m into n. So given a structure, these many ways I can fill it. And how many such structures are there? These many structures are there. Therefore the total number possible is n into m power n, m into n. Now this is how you are getting it. You can still simplify it. As you know the binomial theorem, according to the binomial theorem, if I expand 1 plus 1 whole power n, I am going to get this entire thing, isn't it? How can you expand it? nc0 into 1 power 0 into 1 power n plus nc1 into, right, 1 power 1 into 1 power n minus 1 plus so on. If you keep on writing this, anyway this entire thing is going to be 1. It is nc0 plus nc1 plus nc2 plus so on, right? So this entire thing is going to be 2 power n. So isn't it? 1 plus 1 power n means 2 power n. So this entire thing is going to be 2 power n multiplied with n power m into n. So this is the total number of DFAs that are possible with n states, and with one of them as designated initial state, and it contains m input symbols. Got it? Okay.